Why is Pluto 30 degrees colder than the established laws of planetary physics say it should be? For most of the 20th century, we viewed this world as a blurry, frozen dot at the edge of the solar system, where nothing ever happened. When NASA's New Horizons probe flew past it in 2015, those assumptions vanished. It revealed a world of water ice mountains, flowing nitrogen glaciers, and a layered bluish haze. That layered atmosphere presented a massive mathematical problem. Our existing models of how sunlight interacts with nitrogen suggested the air should have been much warmer than what the probe actually found. This gauge shows the predicted temperature for Pluto's upper atmosphere. Based on nitrogen and methane, the math said it should sit at 100 Kelvin, but the measurement recorded by New Horizons dropped much further. The atmosphere was actually sitting at 65 Kelvin. A 30-degree discrepancy suggests that a powerful cooling mechanism is missing from the standard model. At this distance from the sun, gases alone cannot explain why the air is this cold. If the equations for nitrogen-rich atmospheres are off by this much, it indicates that an unknown variable is dominating the planet's thermal balance. In 2017, planetary scientist Xi Zhang proposed that the atmospheric gases aren't the primary factor in Pluto's temperature. He suspected the haze itself was in control. The process begins when methane molecules in the upper atmosphere are hit by UV light. The energy is just strong enough to break them apart into smaller fragments. These fragments start reacting and sticking together, growing into complex hydrocarbons. Eventually, they clump together into solid, tar-like particles called tholins, which settle into the haze layers we see from space. Zhang's theory was that these solid particles absorb solar energy and then efficiently re-emit it as mid-infrared radiation. They were essentially radiating that energy back into the void. This was a radical departure from the standard view that only atmospheric gases could dictate a planet's climate. Testing that theory required a telescope sensitive enough to detect faint infrared heat from billions of miles away. It took the 2021 launch of the James Webb Space Telescope to get that data. In 2023, researchers used Webb's mid-infrared instruments to isolate the heat signature of Pluto from its moon Charon, a task previous telescopes couldn't manage. When the researchers plotted the thermal glow, the recorded dots matched the energy signature expected from solid haze particles. The icy surface alone couldn't have produced this much infrared heat. The Webb data validates Zhang's model. On Pluto, solid haze particles perform the thermodynamic work that scientists previously attributed only to gases. We now have evidence of a world where solid particles, not gases, are the primary regulators of the climate. This forces a reconsideration of other hazy moons in our solar system, such as Titan or Triton, where we once assumed gases explained the temperature. It also complicates how we study exoplanets. Many distant worlds are cloaked in haze, and if those particles dominate their energy balance, our current gas-based models will lead to incorrect temperature estimates. We may have to adjust how we calculate the surface temperatures of distant worlds. If haze is the primary cooling agent, our current estimates for habitability are likely inaccurate. These freezing skies might actually be a look back at Earth's own history. Before oxygen became a major part of our atmosphere 2.4 billion years ago, Earth was likely wrapped in a nitrogen hydrocarbon haze, driven by the same UV chemistry we see on Pluto. Those ancient particles would have played a significant role in regulating the early Earth's temperature, potentially stabilizing the climate long enough for life to take hold. Investigating why a distant dwarf planet was 30 degrees too cold has provided a framework for understanding our own origins. These haze-driven thermal processes may have been a consistent factor in stabilizing planetary climates across the solar system.